Can you believe this 2.4 GHz 5-channel transmit is controlled by using 80 tiny 13A chip? Let's find out how we do it. For this circuit, mainly I am using 80 tiny 13A as a main controller, NRF24L01 transceiver module and 2 joystick module. If you could remember my 12 channels transmitter video, we use transmitter module that can control with one pin. If pin is high, it will turn on the transmitter, and with the pin low, it will turn off the transmission. But in NRF module, things are little bit different. It doesn't have an input pin like 315 MHz module. Instead of that, it has 6 pins including an SPI interface. So in order to use this module as a transmitter, we have to push relevant configuration and transmitting data via this SPI interface. Okay, problem number 1. Since we are using 80 tiny 13A, there is no an SPI peripheral in this chip. So we need to implement SPI control in our code. Problem number 1 is solved. Now problem number 2. NRF has 6 pins for communication with microcontroller, and the 80 tiny 13A chip also has only 6 pins. So there is no pin for channel inputs. Okay, datasheet time. We can observe that there is a TX buffer in this module. After we load the transmitting data to the TX buffer, we should give at least 10 microsecond pulse to CE pin, and it will transmit one data in a TX buffer. But if we keep CE pin in high state, it will send all data in TX buffer and enter standby 2 mode until we upload another data to the TX buffer. Then it will again transmit in and enter the standby 2 mode. That means we can pull up this pin via a resistor without affecting our application. Now the CSN pin need to pull down during SPI operation, and it should pull up after that. So I am adding a pull up resistor to it. But how we pull down it while the SPI operation? Let's see. For the clock pin, we have to give clock pulses to write or read the SPI data. And if we connect both pins through a diode like this, it will pull down the CSN pin while negative cycle in the clock pulse, and it will pull up again via this resistor in positive cycle of the clock pulse. Therefore, we need to delay the voltage rising beyond the threshold voltage of the CSN pin until the next negative cycle of the clock pulse. So adding a capacitor like this will do the job. Since I am not going to read data from NRF, I can remove MOSI connection. Now I have 3 pins for inputs, and I am using those as analog inputs. The joysticks are connected like this. For this circuit, I use reset pin as analog input, and it is pull up via 4.7 kilo ohm resistor to prevent the reset state. For 3 channels, I connect 3 switches via different resistors like this. As on diagram, I made homemade PCB for my convenience. Now open the Arduino IDE and start a new sketch. First of all, I am define the input and output pins for convenient. In the setup function, I am assigning IRQ pin as input, then the MOSI and SCK as outputs. As on our circuit diagram, in order to apply logic high to the CSN pin, we need to apply high to the SCK pin. So I initially write digital write high to SCK pin. Then I am writing the clock pulse function. This will turn on the SCK pin and immediately turn off it. Now I write SPI data 1 and 0 functions. For data 1 function, we should put MOSI at high level before the clock pulse. For data 0, we need to pull down MOSI before clock pulse. After that, I am writing SPI byte write function like this. It will continuously write 8 data bits as the receiving value to the SPI byte variable. For an example, if I call this function by throwing value 0x0f, then it will working like this. To push the configuration data to the NRF module, we need to continuously write 2 bytes as command and data. So I am writing function like this. In this function, first of all, I am disable all the interrupts. If you can remember, to pull up CSN pin at idle state, we always kept SCK pin at high level. But in order to write data to the NRF, we need to pull it down. So I am writing digital write low to the SCK. To give enough time to discharge this capacitor and the CSN pin pull down, I need to add some delay. But initially on this function, I disable all interrupts. So I cannot use Arduino delay functions. Therefore, I am writing delay functions like this to add small delay. Then I am calling SPI write bytes function by throwing command variables value to it. After that, I am calling the same function by throwing data variables value. Then we need to pull up the CSN. So I write digital high to the SCK pin and add my delay to give enough time to charge the capacitor and pull up the CSN pin high. At the end of this function, I enable the interrupts again. If I call this function by putting command as 0xf0 and data as 0xA6, it will work like this. To write 5 bytes address, I am writing the function like this. This is also working like SPI write configuration function, but this will continuously write 5 bytes after the command byte. If you are use 3 or 4 bytes for address, you can customize this function. Now I am writing NRF initialization function like this. In this function, I am writing configuration to the NRF module. And to write particular configuration data to the relevant address on the NRF, it need to set the 6th bit of the address. So if I wanted to write the config address, which is address 0, I have to set the 6th bit and then the command would be 0x20. After that, the particular data bytes. This is for enable transmitter and transmission complete interrupt. After I write enable data, it should put at least 1.5 millisecond delay to settle. So I am putting 2 millisecond delay before my next instruction. You can check all these values from the data sheet. In this transmitter, I am going to transmit 3 pins analog read values as 3 bytes. So I am writing my transmit functions like this. This is also same as previously wrote function, and the difference is I am writing 4 bytes for SPI. First one is the command to the write to the TX buffer, then the rest of 3 bytes are analog read values. Then I'm waiting for about 1 second to interrupt pin goes slow to confirm the transmission completion. At the end of this function, I clear the interrupt flag and the TX buffer. All functions are completed now. Then back into the setup function. As on the datasheet, waited about 100 milliseconds before any instruction. Then call the initialization. As mentioned previously, in our main loop, I read analog voltage in the inputs and then transmit those values. But both joysticks are at idle position and all three toggle switches are at off state, it should not transmit. If all toggle switches are off, then the analog value should be greater than 250 after we map it within 0 to 255. As well as if the joysticks are perfect, then the analog reading should be nearly 511. After we map that value between 0 to 255, we should get it as 127. Therefore, I am writing my main loop like this. Now our transmitter code is completed and ready to program the chip. You can download the same code with comments from my Patreon page that I attached the link to the description. It will be great support for me to fund the future projects like this. If you have any suggestion on this video, please leave a comment, and also please make sure to subscribe our channel. We will meet again with our receiver circuit video.